In this video, I'm going to start discussing some algorithm basics, and in particular in this video I will be discussing the big O notation, which is a measure of the algorithm complexity. So it's a measure that evaluates the count of operations, so the number of operations, which is roughly the number of steps that an algorithm has to take to execute the algorithm. And so when we evaluate the complexity, we want to speak on the order of the operation count, not the exact count. So we're not that interested in exactly how many steps it took, just sort of the order of magnitude really is what we are interested in. Then this quote here from Geeks for Geeks, so this link right here, just says that there's often a trade-off between optimal memory use and runtime performance. And so a lot of times if you have good runtime performance, you are taking up more memory use. And if you have better memory use, then you might suffer in the runtime performance. All right, so there are three things we tend to want to look at when we are analyzing algorithms, and that is the best case, worst case, and average case number of steps for our algorithm. So the best case is just the fewest, worst the most, and the average is the average. And so if we are, say, looking at a linear search for a particular value in an array that has 10,000 elements, so these are integer elements, and we're just looking for a single number, a single integer value in that array. Then we have the best case, which is that the value is the first element searched, so it'd be in like the 0th index of the array. And so it only took this single elementary operation. The worst case is that the algorithm has to search the entire array and take 10,000 elementary operations in order to find the value that you are looking for in the array. The average case is that it just takes 1 plus 10,000, so 1 plus n over 2 elementary operations. And so that would be, for this 10,000 element array, about 5,000, well, it would be 5,000 operations. As we see that this is linear, since if we doubled the number of array elements, then we would just multiply this by 2, and we'd have essentially 20,000 here divided by 2, and so it would be 10,000. And so doing this sort of brute search approach here to searching our array is going to be linear, and so we would use this big O with an N in parentheses like this, and that is the linear type right there. But if we try what's called a binary search, then we will do the following. And so this is essentially what a binary search does. So we sort the array in ascending order. This is just sort of a first step. This binary search only works if our array is actually in ascending order. And so what it'll do is it will look at the middle element of the array, and it will test whether it's greater than, equal to, or less than the value of interest. If it's equal to it, then that was sort of our best case scenario, and it just outputs that index, and it's finished. So it found the value on the first step, and that would be the best case scenario. But say our value of interest is greater than that middle value, then it will go down here, so it'll set the lower index to the middle index. So our lower index is now the middle index plus 1. And so what that is doing essentially is it's cutting off the bottom half of the array. So we're now only looking at all the elements on the top half of the array, because we saw that our our value was greater than that middle one. So this is why it needs to be sorted in ascending order. I mean, I guess you could do descending order and then you just flip what I'm talking about here, but we're talking about in ascending order. So it sees that this middle that the value we're looking for is greater than the middle element. So it knows that we only need to look in the top half of the array. So it will cut that off and then it will sort of go back here, compare the middle element of that new one, and say now that it finds that it's less than, the value is less than the middle element. So now it'll set the upper index to the middle index -1. And so then it will look at sort of the bottom half of that array. And so remember, in the second step, we're already looking at just the top half. So now we're looking at the bottom half of the top half. So we're looking at just a quarter of the array. And then it'll keep iterating through this until it finally finds the index for the value that we are interested in. So you can see that kind of up here with this image right here. So if we have this 7-element array and we search for 3, so the middle element is 4, so it knows that the element we're interested in is less than that. And so it sets the upper element to the middle -1, which is 3. And so now it looks and it finds 2 right here. And it sees that the element is greater than that. And so then it sets that to being +1, so 2 plus 1. And so now we're left with just 3. And so now it has found 3, and so it took 1, 2, 3 steps right here in order to find that. So the first step is just looking at this one, then we split it, look at this one, then we split it, look at this one. And so it took that many steps to get to it, and that would be a worst case scenario for something like this. All right, so looking again at our 10,000 element array. So with this binary search, our best case, again, is that we just find it on the first try. So it just happens to be the middle element there. And so it just took this single elementary operation. Where the worst case is that the algorithm has to search the entire array. And so it would take log of base 2 of 10,000, which would be 13 elementary operations. Then the average case would be that it's log base 2 of essentially 10,000 divided by 2, which is 12 elementary operations. And so we can see that this is a logarithmic time complexity for this. And so I am putting this base 2 here explicitly, but quite often when you see this, like in the literature, they neglect to put that base 2 there. But for something like a binary search, it would be base 2 on there. And so here are some of the different time complexities we can have. We can have constant here, which means it just takes a constant number of steps for performing the operation. And so it doesn't depend on the size of the input. We saw our logarithmic here, so it just takes a log of n number of steps, where the base of the logarithm like this says, is most often 2. So performing a given operation on n elements. So if we had, say, 1,000,000 elements, then then it would take about 20 steps right here for that, with 1,000,000 elements there. We saw for our 10,000 it was 13 steps. So then linear, here we have 2 different kinds of linear. So this is the kind we were talking about above, where it takes the same amount of steps as the number of elements or the number of inputs. So we had, our 10,000 element array, so it was an input of 10,000. And so it took just the number of steps that it took to find the number. So whatever the number was in the array, it took that many steps to get to it. But you can also find this O of n times log of n, which is just a little bit worse than this one. But then we get up here to our polynomial time, so things like quadratic and cubic here. So if you have, say, like an n number of input, then it would take n squared number of steps or n cubed number of steps. And then we have exponential, which is the worst kind here. And so this would be like 2 to the n or n factorial or even n to the k or n to the n right here. And so even just a small increase in the input size will greatly increase the number of steps. And so we see those functions right here. So this is our input size on the x-axis and the number of operations here on the y-axis. And so we see like this factorial here is going to just shoot up really fast right here. Then we have our 2 to the x right here. And that's going to shoot up really fast. Our x cubed and x squared are going to shoot up. We have this n log n here that's going up. Then this n here, which is just going up linearly. And then this one kind of flattens out a bit here. And then this one is just steady. And so this is looking at some times over here for a circa 2008 computer, which would have about 50 million elementary operations per second. And up here in bold, these are the input sizes. And so we see, for these ones right here, even up to 100,000 elements, it's still going to take less than a second. But then when we get up to this quadratic time here, when we get up to 10,000 and 100,000, we start seeing an increase in the amount of time it takes. And then with this cubic here, we start seeing that even at 1,000, it's 20 seconds. Then 10,000, it's over 5 hours. And then here, it's practically a year long for this to go. Then we see here for this 2 to the n, even with just 50, it's taking 260 days on here. Then we get these hangs, which means that it's essentially just taking so long that it's not going to ever finish really. And so we see that these ones, these right here, this 2 to the n, n factorial, and n to the n are quite bad, and so we want to avoid those. In fact, usually this n squared, so this quadratic here, is about the worst you want to do. So when you're trying to make an algorithm, if you can get it below quadratic n squared here, you're usually doing pretty good, where n squared is kind of the maximum badness, the worst that you would ever want your algorithm to perform at. And so anything sort of beyond that is usually going to be considered kind of a bad algorithm. All right, and so again, looking at our 10,000 element array, we can look at some times here. So again, we saw above that with our 10,000 elements that it takes. So if we get it on the first try, it's essentially 0 to finish the search. And so we see this is an output right here. So the target found. So we're doing a 10,000 elements, and we're looking for element 5,000 right here. And so this took about 4 milliseconds right here. And then we do the binary search, and again, this took about the same amount of time as our linear search with 10,000. But then if we do it with a million right here, we see that the binary search took about 2 milliseconds, where the linear search took almost 5 milliseconds right here. And so that is with an input of a million. And we can actually look at this here with something even larger. So I have this linear search algorithm right here, which is just iterating through with this for loop here, and then it's just if that element is equal to the target, then it's finished and we break. Whereas if it's not, then we just increase this count to keep track of how many operations we're doing and iterate back around. And this right here is just for if the target number is not found. And so we're using these date time things here to measure the time that takes. And down here is our binary search. So we see that while our min is less than or equal to our max, which we have to do because we see that we're reducing and increasing these through these iterations. And so while min is less than or equal to max, this will keep iterating. Then we get this mid, which is just halfway between the min and max. This first if up here, so if the target is just equal to the array element at the middle index there, then it's finished, and it'll print this out and break the loop right there. But if it's less, if the target is less than that middle one, then we set the max equal to mid minus 1. And so we're cutting off that top half of the array. Where this one, if the target is greater than, then we set the min equal to mid plus 1. So we're cutting off that bottom half of the array. And so this will keep going until we find that element. And so what I'm actually using here, so this is an array that is a size of 1 billion here. So we're looking at a billion. And then this will search for a random number here between 0 and this 999,999,999 here. And so it will look for a random number between there. Then these are just running those two algorithms. And so if we run this, we see this will take a little bit because it has to populate that entire array, and then it's going to search for this number, which is about 228 million. And so we see that with the linear search, this took about 0.7 seconds, where with the binary search, this took considerably less. So this took, these are like the milliseconds right here, so it took even less than that. We see it found it in 28 steps. So the worst case scenario for a binary search on a billion elements is 29. So this found it in 28. So we can try running this again. Again, it'll take a little bit for it to populate that array. So we are searching. So this number is not that much different than last time, but we see this took about 0.97 seconds, where this took quite a bit less, but it did find it in 26 steps. So let's try running this again. So we wait for it here for a moment. Now it's going to look for something quite a bit bigger. And so we see now that the linear search, because it's starting from the lowest number and just iterating through up to the highest number. It now took almost 3 seconds to do this, whereas our binary search, which did it in 27 steps as opposed to this, 867 million some steps, found it in less than a millisecond right here. And so we can see that this binary search is doing it quite a bit faster than that linear search. So especially when you start getting to these much larger numbers, we saw in the presentation here that even with a million, with n equals a million here, it was really, the binary search was really only about twice as good as the linear search, where it's sort of orders of magnitude better when you get up to an input size of a billion. But anyway, that is just a little bit on this big O notation and algorithm complexity. So in the next video, I'm going to look at a few sort of specific but simple algorithms that we can just sort of analyze and look at how they work. Yeah, anyway, I hope you found this video helpful, and I will see you in the next one.